Okay, now that we have that foundation in place from the previous discussion in terms of linear optics, we can start thinking about how we would generalize the Mueller matrix concept into a Mueller tensor framework. And the Mueller tensor, again, just like it would be for a Mueller matrix, it's a very general way of handling all 3-photon, or more specifically 6-wave mixing processes, which include second harmonic generation, in the presence of partial depolarization, along with 2-photon fluorescence, and anything where you're measuring intensity out for 2 driving incident electric fields, or incident intensities. So we'll build on what we had in place for linear optics, and what we'll see. I'm going to start with the final conclusions, and that is that there's really this simple one-to-one correspondence between the expressions that we have that are established from linear optics for relating the Mueller matrix and to the Stokes vectors, and what we generate in nonlinear optics. So by definition, really, the Mueller matrix is this Stokes transfer matrix that generates in linear optics an outgoing Stokes vector for an incident driving Stokes vector. And in nonlinear optics, we have the analog, where we have an outgoing some frequency vector that's driven by 2 Stokes vectors for the incident polarization state. And in linear optics, we found that we could reduce this down, at least for the purely polarized component. It could be reduced down to the simple Kronecker product of Jones matrices. And in nonlinear optics, it's the exact same thing. It turns out that the Mueller tensor can be broken down and described for the purely polarized component as a Kronecker product of Jones tensors. And this A term is just this matrix that relates the electric fields to the Stokes vector. And so that's what we're going to show throughout the course of the next couple of minutes. How do we get there? Well, this is our starting point. This is really the definition of the Stokes tensor, the Mueller tensor for Stokes inputs and Stokes outputs. And we're going to use the exact same approach we took before. If we know that we know that we can make the Stokes for the sum frequency by taking this transfer matrix A and multiplying it by the Kronecker product of the electric fields, we can then substitute for the electric fields, bearing in mind the fact that they're related to this chi2 tensor element, and get this expression right here, which on the surface doesn't really help us very much. It looks kind of complicated, right? Because you have a tensor that is then Kroneckered, a tensor multiplied by 2 fields, and then Kroneckered with another tensor multiplied by 2 fields. You throw up your hands and think, man, I don't know how to keep track of all of that stuff. But it turns out that there's some really nice ways you can take advantage of identity relationships. And I won't go through the detail of where these come from, but you can see them in the primary textbook. It's in the appendices to see how they were derived. So at any rate, we can take something that looks just like this product over here and simplify it. We can break it down into a new tensor given by the Kronecker product of the 2 tensors multiplied by the rightmost arguments and then their Kronecker product. And I guess it's actually almost easier to see in the specific example than it is in the general case, but using this identity relationship, we can pull these 2 tensor elements together and then group these 2 and group those 2 as separate Kronecker products and arrive at this expression for the sum frequency sum frequency Stokes vector. It's written in terms of electric field components because, of course, we started with this Jones framework. We can use the exact same trick we used in linear optics by substituting in, for this product for A, for example, we'll substitute in A inverse SA, and that's exactly shown here. So if we have this, if this is A and this is A, then we can substitute SA times A inverse for this product of fields. And if we do that, then we can put that in there, and we can put that in there. So that's just a straightforward substitution. And now we're again seeking yet another identity relationship, hopefully from our toolkit. And in this case, the identity relationship allows us to fold the C and E into a new tensor that incorporates those as well. So, and that's just this identity relationship saying that we have now a new chi2 tensor that was the old one multiplied by these pre-factors in front of the S. In this case, the A inverse matrices. And if we do that substitution, we have this relationship, which, if you look at everything inside the brackets here, gives us, this is our polarization, our Stokes transfer tensor. It gives us the sum frequency Stokes vector out for the 2 driving Stokes vectors, and so that really is M2. And that's a really nice, simple relationship for describing and connecting the Mueller tensor given by M2 and the Jones tensors given by Chi2. And that's where we'll stop for this part. The next step is going to be doing something, I think with vectorization. If I could be wrong, I could be right. But we're going to now take advantage of this expression for the purely polarized component, and then ultimately, throughout the course of the next couple of these vignettes, reduce it down into to an invertible system where we can recover the elements of the Mueller tensor directly. And that's where I'll stop for now.